Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Laplace transform of derivatives and Laplace transform of integrals. Let's begin. Laplace transform of derivative of a given function. Derivative of the given function f of t as f dash t, its Laplace transform is equal to s into Laplace transform of that of function f of t minus the value of that function at 0. Here we know Laplace transform of f of t is equal to capital F of s. Therefore, in place of Laplace transform of f of t, we write s into f of s minus the function at 0. This is the Laplace transform of derivative of a given function. We have to prove Laplace transform of f dash t, first order differentiation of that given function. According to the definition of Laplace transform, 0 to infinity e to the power minus st, the function as f dash t dt. That type of integral can be solved by using by parts method. By using by parts integration method as the formula uv integration with respect to dx as v dx integration u minus integration over derivative of du by dx integration of v dx. Here we choose v is equal to f dash t and u is equal to e to the power minus st. That integral can be solved. E to the power minus st f of t limit from 0 to infinity as the integration of f dash t with respect to dt, the result will be f of t minus 0 to infinity derivative minus s e to the power minus st of the function f of t dt. Using upper limit and lower limit, when we first put in infinity at t, the result will be 0, and when we put 0, that we have the function at 0, minus minus plus s as constant, that will be to outside, integration from 0 to infinity e to the power minus st f of t dt. As that case, the limit t tends to infinity, the value of e to the power minus st f of t will be 0. So, at infinity that value will be 0, and at 0 the function is evaluated at f of 0. Therefore, the Laplace transform of derivative of the function f dash t is equal to s, that term as Laplace transform of f of t minus the function is evaluated at 0. As we know, integration from 0 to infinity e to the power minus st f of t dt is equal to Laplace transform of the function f of t from the definition of Laplace transform. Let we extend that particular equation. In extending, we have, if we have to calculate the Laplace transform of the second order differentiation of a given function, Laplace transform of second order differentiation of a function, then same thing, S Laplace transform of f dash t minus f dash 0, taking the second order differentiation, Laplace transform of that second order differentiation function by considering that kind of expression, which is equal to S Laplace transform of f dash t, that expression as S Laplace transform of f of t minus f at 0. So, we have Laplace transform of f dash t is equal to s square Laplace transform of the function f of t minus s at f of 0. Okay, minus f dash 0 minus f dash 0, the second order differentiation function Laplace transform. Look at that expression. Similarly, also Laplace transform of third order differentiation function, that is S L Laplace transform of second order differentiation function minus S double dash 0. So, put at the values of Laplace transform of f double dash t as s whole into s square Laplace transform of f of t minus s f at 0 minus f dash at 0 minus f double dash 0. In place of Laplace transform of f double dash t, we put these values. Therefore, we have Laplace transform of f triple dash t, Laplace transform of f triple dash t as SSQ Laplace transform of f of t minus s square f at 0 minus s f dash at 0 minus f double dash at 0. Similarly, by induction, we have the Laplace transform of, that is the Laplace transform of third order differentiation function, then Laplace transform of nth order differentiation function is equal to SQ, that is n, s to the power n, L Laplace transform of the function f of t minus s n minus 1 f at 0 minus s n minus 2 f dash 0 minus s n minus 3 f dash 0 up to f n minus 1 and 0. In this way, we say that one is the Laplace transform of nth order differentiated function. So, we have studied here Laplace transform of derivative. Next, Laplace transform of integrals. Laplace transform of the integral, that integral is given as the limit from 0 to t f of t dt. The result as 1 by s f of s, whereas f of s is the Laplace transform of f of t. Now we prove the Laplace transform of integrals. We know that f of s, which is the Laplace transform of the function f of t. Let us consider another function, a function which is phi of t, that is denoted by integration from 0 to t f of t dt. Therefore, phi is 0, phi at 0 it will be 0, and its first order differentiation will be f of t. From the Laplace transform of a derivative, we have Laplace transform of derivative function phi dash t is equal to s Laplace transform of phi at t minus phi at 0, which implies Laplace transform of ft is equal to s Laplace transform of, in place of f dash t we substitute f of t. Similarly, in place of f of t, so Laplace transform of phi of t minus phi of 0 value as 0, as we taken that substitution here, which implies Laplace transform of f of t is equal to s Laplace transform at phi of t which implies 1 by s to that side, Laplace transform of the function f of t is equal to Laplace transform of phi of t. Therefore, we have Laplace transform of the function as phi of t is considered 0 to t f of t dt is equal to that much 1 by s Laplace transform of f of t. That one is equal to 1 by s f of s, which one is proved, the Laplace transform of integrals. Next, we have to extend the Laplace transform of derivatives and Laplace transform of integrals if we multiply by t, then what happened? So, here we apply the derivative of Laplace transform. If the Laplace transform of the function f of t is equal to f of s, then Laplace transform of t to the power n f of t is equal to minus 1 to the power n, its nth order differentiation with respect to s of the function f of s. That can be proved. Laplace transform of f of t is equal to f of s from the definition, that is 0 to infinity e to the power minus st f of t dt. Let me differentiating that with respect to s, differentiating above equation with respect to s, we get d f of s with respect to ds, which is equal to d of ds at the integral 0 to infinity e to the power minus st f of t dt, which is equal to integration from 0 to infinity d by ds e to the power minus st f of t dt, 0 to infinity minus t e to the power minus st f of t dt, its differentiation with respect to s, which is equal to 0 to infinity e to the power minus st minus t f of t dt. From the definition of Laplace transform, that one is the Laplace transform of minus t f of t. Hence, we write Laplace transform of t f of t. That negative sign is multiplied, we have minus 1 d by ds of f of s, then Laplace transform of t square f of t is equal to minus 1 square second order differentiation with respect to f of s. Similarly, it proceeds as Laplace transform of t to the power n f of t, which is equal to minus 1 to the power n nth order differentiation with respect to dsn of the function as f of s. In this way, we extend the derivative of Laplace transform as multiplication by t. Next, division of t, we use integration of Laplace transform. If the Laplace transform of the given function f of t is equal to f of s, then Laplace transform of 1 by t f of t is equal to integration from 0 to infinity f of s ds. When t is multiplied to that of given function, then it will be derivative of Laplace transform, and if t is divided to that of given function, then it will be the integration of Laplace transform. We have to prove, as it is given Laplace transform of the given function is equal to f of s from the definition of Laplace transform, integration from 0 to infinity e to the power minus st f of t dt, the given function multiplied with e to the power minus st. Now integrating above with respect to s, we get integration from 0 to infinity f of s with respect to ds, integration from 0 to infinity, integration from 0 to infinity e to the power minus st f of t dt with respect to ds is equal to integration from 0 to infinity f of t integration from 0 to infinity e to the power minus st ds with respect to dt is equal to integration from 0 to infinity f of t, then that integral as e to the power minus st divided by minus t using the limit from 0 to infinity with respect to dt as the integration from 0 to infinity, that one is equal to integration from 0 to infinity minus f of t divided by t e to the power minus st, the limit from 0 to infinity dt is equal to 0 to infinity minus f of t divided by t using upper limit and lower limit, it will be 0 minus e to the power minus st with respect to dt, then integration from 0 to infinity e to the power minus st minus minus plus 1 by t, the function f of t with respect to dt. According to the definition of Laplace transform, that one is the Laplace transform of 1 by t, the given function f of t. Therefore, we have Laplace transform of 1 by t of given function f of t is equal to integration from 0 to infinity f of s ds. So, when t is divided to that of function, then we use integration of Laplace transform. Now, taking some examples related to derivatives and integrations of Laplace transform. Find the Laplace transform of the given function, that is integration from 0 to t e to the power minus t cos t dt. That type of problem can be solved by taking Laplace transform of integrals. So, the solution, the given function f of t is equal to e to the power minus t cos t. Therefore, taking the Laplace transform of f of t, which one is equal to Laplace transform of the function e to the power minus t cos t, e to the power minus t cos t Laplace transform, as usual s plus 1 divided by s plus 1 square plus 1, as we studied the Laplace transform of some elementary functions using a plus b whole square formula, s plus 1 divided by s square plus 2s plus 1 plus 1. So, s plus 1 divided by s square plus 2s plus 2. Let we using the theorem of Laplace transform. Therefore, using the theorem on Laplace transform of integrals, we have Laplace transform of integrals 0 to t e to the power minus t cos t dt is equal to 1 by s plus 1 divided by s square plus 2s plus 2. So, the Laplace transform of 0 to t e to the power minus t cos t dt is equal to, that s is multiplied, we have s plus 1 s whole into s square plus 2s plus 2. here we use just Laplace transform of integrals. That question is solved. Next, find the Laplace transform of the function as sine under root of t is given under root of pi divided by 2 s to the power 3 by 2 into e to the power minus 1 by 4s. The value of Laplace transform of cos under root of t divided by under root of t we have to found out. So, the solution, let choose a function f of t as sine under root of t. Therefore, its first order differentiation f dash t is equal to cos under root of t divided by 2 under root of t. Also, f at 0 is equal to 0. Using Laplace transform of derivative, Laplace transform of derivative f dash t is equal to s Laplace transform of the function f of t minus the function is evaluated at 0, which implies Laplace transform of f dash t as cos under root of 2 t divided by 2 into under root of t is equal to s Laplace transform of f of t as usual f of t sine under root of t, given that value s into under root of pi divided by 2 s to the power 3 by 2 e to the power minus 1 by 4s. The function evaluated as f of 0 is equal to sine 0 0 0, which implies constant to outside Laplace transform of cos under root of t divided by under root of t is equal to half under root of, we can write it as pi s under root e to the power minus 1 by 4s, which implies we have to found the value of that function's Laplace transform. So, Laplace transform of cos under root of t divided by under root of t is equal to, that 2 is multiplied here, so 2 to cancel out, pi by s under root e to the power minus 1 by 4s. That one is the required result of the Laplace transform of that given function. So, with the help of this video lecture, we understand Laplace transform of derivative, Laplace transform of derivative of nth order differentiated function, Laplace transform of integrals. Extending this, as when we multiply t to a function, we use derivative of Laplace transform, it is proved, and when we divide t to that of given function, we use integration of Laplace transform, and we have then two problems related to derivative and integration of Laplace transform, and its solution is calculated by using the concept of derivative and integration in Laplace transforms. So, with this useful and informative notes, let me wind up this session. Thank you.